a fixed set of nuclei where we will optimize, for which we will optimize the electronic coordinates. So these kind of methods are called as the electronic structure methods, where we will be solving the time-independent Schrodinger equation, which is the normal eigenvalue equation xi is equals to E psi. Whereas the second scenario includes for the moving nuclei, where we will be considering the optimization of the electronic coordinates for at each and every nuclear time step. So these kind of methods are called as nuclear dynamics methods, and we will be using either the time-dependent Schrodinger equation or with various approximations, its variants, in order to simulate the nuclear dynamics methods. For the purpose of the today's presentation, we can consider or we can divide this non-adiabatic dynamics methods into two ways. The first one is the adiabatic dynamics methods, where the wave function can be represented as a single potential energy surface. In other words, the nuclear motion is governed only by a single potential energy surface. Whereas the non-adiabatic dynamics methods include the expansion of the wave function, or we can say that the wave function cannot be represented by a single potential energy surface. There we need to have more, the wave function is like a superposition of more than one potential energy surface, and accordingly the nuclear motion is governed by many potential energy surfaces. While there are several software packages in order to simulate the adiabatic dynamics, simulating the non-adiabatic, the on-the-fly implementation of non-adiabatic dynamics methods is pretty scarce. And as I will be showing, we have implemented one of the non-adiabatic dynamics, a few of the non-adiabatic dynamics methods in the DFTB plus package. So here is the brief outline of my talk. I will be showing a few applications of the non-adiabatic dynamics as well as the adiabatic dynamics. If time permits, I will also go through the electronics, few examples of the electronic structure methods applications. If not, I'll directly go on to the ongoing works that I'm doing at the IIT-Madras along with the possible areas of collaboration. Moving on to the first application. So here we will be discussing the non-adiabatic molecular dynamics application. So the wave function should be represented in terms of the several potential energy surfaces. So in this particular application, we have studied the electron dynamics. So we captured this electron dynamics by implementing the non-adiabatic dynamics method known as the fewest switches surface hopping method in the DFTB plus package. So here we used the electronic structure method as the DFTB itself. So our Hamiltonian, when we are trying to expand, we are using the DFTB, and we captured this electron dynamics using this non-adiabatic dynamics method known as the fewest switches surface hopping. So here I am showing you in this video the electron dynamics that has been captured using this method. We can clearly see that, So you can clearly see that on the right hand side we have this phthalocyanine molecule, which is like a donor molecule, and on the left hand side we have a fullerene molecule. What we have seen in the video is an ultra fast charge transfer of the electrons from the phthalocyanine moiety, which is the donor moiety, to the acceptor moiety, and we simulated this using this fewest switches surface hopping methodology. So we got motivated by the ongoing debate on the mechanism of exciton dissociation at the donor acceptor interfaces of an organic photovoltaic system. So a typical bulk heterojunction would look like as shown in this figure. Excuse me 1 second. So as shown in this figure, where both the donors as well as the acceptors will be miscible at various proportions. So this is like an atomistic view of such a bulk heterojunction. So the typically accepted mechanism for the exciton dissociation in the organic photovoltaic system is we will be having, once we start shining the light, there will be generation of the excitons either at the donor or at the acceptor phase, and these excitons will be migrating towards the interface where they will be separated into the charge transfer state, and this charge transfer state either can be further, these charges can be further separated in order to form what is known as the charge transfer to charge separated state, or these charges can recombine. However, there is both experimental and theoretical results which are supporting different kinds of mechanisms for this formation of the charge separated state. So some of them include the direct exciton. So this exciton will be directly converted into the charge separated state, or they can form the hot CT states. These are like vibrationally excited states we can see, and from there it can be forming the dissociation state and so on and so forth. So in order to resolve this debate, one needs to have a non-adiabatic dynamics method which can help to exactly pinpoint what is the exact mechanism. So here we try to implement one of that non-adiabatic dynamics methods in the DFTB plus package, and the current work is just the first step towards realizing that goal. So moving on to the methodology. So as mentioned, our aim is to simulate the charge transfer dynamics as such. So in order to do that, first we need to solve the time-dependent Schrodinger equation in order to obtain the time-dependent wave function, which is psi of r comma t. So here we are using this time-dependent electronic Schrodinger equation in order to obtain this psi of r comma t, and we will be numerically integrating this time-dependent Schrodinger equation. So once we have, so although we are saying that psi of r comma t is a wave function, it's much like any vector. This is like an abstract vector in the space. So in order for us to define this vector, we need to have the components as such. So how do we get the components? First, we need to have the basis. And once you have the vector, you project this vector onto the basis in order to get the components. So similarly, here we are using what is known as the Born-Oppenheimer ansatz in order to expand the vector. This is the wave function in terms of the instantaneous eigenstates that we can obtain by solving the time-independent Schrodinger equation. That is the eigenvalue problem xi is equals to E psi, where you will be just diagonalizing this matrix in order to obtain the eigenvectors. So these eigenvectors, you can assume them as molecular orbitals or S0, S1, and so on states. These are the ones that we will be using in order to expand the complete system's time-dependent wave function. So once you have the wave function, these expansion coefficients, you can visualize them as the components of the vector. These are the ones which are the adiabatic populations, like the state populations are these ones. So once you have these ones, you can project them onto the atomic orbitals in order to obtain what is known as the charge population. So this is the procedure that we have implemented. So first, in order to obtain a differential equation that we can numerically solve, we have projected this phi i's, which are nothing but the molecular orbitals, by expanding this ansatz into this first equation, which will give us roughly this a differential equation. Here, the second term is the most important one, which contains two indices, J and I, which corresponds to the transfer of electrons from one state to the another state. So this is the one which corresponds to the electron transition between the potential energy surfaces, and this is what is generally known as the non-adiabatic coupling. So this is the one which is responsible for the electrons to transfer from one state to the other. And since this is a differential equation, we need to have an initial condition. Here, the initial condition we consider as the LUMO of the donor. So the electron donating molecule's LUMO is considered as the initial wave function, and then we propagated this differential equation using we integrated the differential equation using the fourth order Runge-Kutta method. We are also under the classical path approximation, which essentially means that the back reaction of the electrons will not be there. And as mentioned earlier, these eigenvalues, eigenvectors, etc. were solved using the normal DFTB Hamilton. So coming to the non-adiabatic dynamics method, as mentioned, we have used what is known as the fewest switches surface hopping method. So this is a phenomenological model which assigns a probability known as the Gij, which will be, once we assign this probability, we will be able to compare it with a random number, which essentially says that whether an electron can go from ith state to jth state or not. So if this Gij, this probability is greater than the random number, then we will allow the electron to hop from one surface to the other surface. That is, after you shine the light, you will accept that, okay, this electron transition can happen. If not, you will just continue to stay on the same state. So here rho ii corresponds to those adiabatic populations, and rho ij corresponds to the adiabatic density matrix, and this is the derivative coupling that we have seen earlier. So going on to the results. So using this FSSH methodology and the DFTB Hamiltonian, we have calculated the non-adiabatic transitions. So on the left side of the figure, I have shown how the energy of the system, how the adiabatic energy states change with time. As you can see, there are several places where these adiabatic energies are coming very close to each other. So these are the places where this transition can occur very easily, and where the non-adiabatic coupling vector also will be very high, which means electron can easily jump from one state to this one potential energy surface to the other potential energy surface. This red color curve that you are seeing corresponds to the non-adiabatic transition, that is the transition from one electronic state to the another electronic state for a specific FSSH trajectory. In order to obtain any meaningful answer, we need to run the simulations for several thousands of FSSS trajectory and several nuclear trajectories as well, because this is a stochastic process and we need to average all of this. So that's what we have done in order to obtain what are known as the adiabatic populations or MO populations. So here this LUMO plus 3 corresponds to the LUMO of the donor, that is the phthalocyanine. So here the LUMO electron population is decreasing, which means the donor is donating or losing its electrons, and that's what we were able to capture clearly. And this LUMO corresponds to the Fullerene's LUMO, that is the acceptor is accepting the electrons. So we could clearly capture that dynamics using our methodology. A better way to represent the same answer is through the charge populations, as I mentioned earlier. So here is the charge population plot. You can clearly see that both the H2PC molecules, which are the donor molecule population, is decreasing, whereas the acceptor molecular population is increasing. Qualitatively, our dynamics also is in well agreement with other ab initio methods. They have also shown that within the first 500 femtoseconds, there is a complete charge transfer from the donor to the acceptor. So in order to further verify our implementation and the methodology, we have also studied with both C60 and C70 molecules, where C60 corresponds to a better electron acceptor when compared to the C70. And we accordingly have seen that it has a slower population rise. So the electrons are like going very slowly to the C70 when compared to the C60. And here the experimental results are shown in the black curve, which are also in well agreement with our theory. We have also studied the similar kind of dynamics and other organic photovoltaic systems, such as the C60 CPC triad it is called, where there is fullerene, carotenoid, as well as the porphyrin. And we have also implemented various other short-term propagation techniques, with other non-adiabatic techniques, such as short-term propagation of TDSE, quasi-diabatic PLDM, etc. etc. With that, I will stop the first application of the non-adiabatic dynamics. Now we are moving on to the second kind of applications, which are the adiabatic dynamics applications. Please remember that in this case, the wave function can be represented by a single potential energy surface. So in these applications, we have considered, for example, the understanding of the various kinds of electrolytes that are useful for the calcium ion batteries. So calcium ion batteries are like multivalent ion batteries that have the potential to replace the lithium ion batteries. And due to the very high reducing power of the calcium, currently there is a lot of research going on in order to predict the proper salts and the solvents that can stay as it is on the calcium surface. Because of its high reducing power, majority of the salts and solvents will decompose on this calcium surface. So we have studied 4 of the salts and 3 solvents, and we find that carborane salt that is shown in here, this carborane salt and glyme solvent are 2 of these salt and solvent combinations that can stay undissociated on this calcium surface. So these ab initio molecular dynamic simulations also helped us to understand why these molecules or the salt molecules are completely dissociated. If you are doing a simple electronic structure method, so these molecules will be showing to be very stable. On the other hand, experiments clearly show that they will be dissociated, and that's what is captured when you are using the molecular dynamics simulations. We have explained these results using what is known as the time-dependent projected density of states. So using that, we were able to exactly pinpoint why these molecules are dissociating. So another application of the adiabatic molecular dynamics include the dissociation of these perfluoroalkyl substances. So here we have considered the harmful pollutants. These perfluoroalkyl substances are harmful pollutants that are present in the water and that are present in the drinking water resources all over the world. Already these perfluoroalkyl substances are banned in both USA and various European countries. However, they are not yet banned in India. So as such, studying how to degrade these molecules is very important. So we have considered these perfluoroalkyl substances and we have added the electrons to this system containing perfluoroalkyl substance and the water moiety around surrounding it, like a solvent moiety that is. So, and then when we simulated, we did see that these electrons, additional electrons, can help to degrade this carbon-fluorine bonds. Remember that carbon-fluorine bonds are one of the strongest bonds that can be formed by a carbon atom. And we observed that in these systems, the trans elimination, when you add 2 electrons, two of these carbon fluorine atoms can be broken. And while describing the reaction mechanisms, we did find that the trans elimination is one of the important ways to degrade this system when compared to the opposite cis elimination. Moving on to the other kinds of examples, we have also used this adiabatic molecular dynamics in order to understand the catalysis reactions, such as the formation of ammonia under the plasma atmosphere. So here our experimental collaborators have synthesized, have seen that there is a very weak catalyst dependence when they are using this low temperature plasma in order to form the ammonia. Then what we have done is, like, we considered both the copper as well as the platinum surfaces, and we collided these surfaces with a pre-adsorbed material like either hydrogen or nitrogen. We have first passivated the copper and platinum surfaces, and then we started colliding this system using hydrogen or nitrogen. So what our simulations have suggested is the very weak catalyst dependence is because of the different kinds of mechanisms that have been observed on the copper as well as on the platinum. On the copper, it is the alliradial mechanism, which just means that the incoming nitrogen molecule is able to directly interact with the hydrogen atoms that are present on this copper surface, and it can form the ammonia molecule. Whereas on the case of platinum, the hydrogenated surface, if you are impinging onto the hydrogenated surface, if you are impinging a nitrogen atom, that will be just adsorbed there, as shown here. On the other hand, if you consider the saturation with NH groups, like as I have shown here, then if you start impinging either with hydrogen atom or with a nitrogen atom, we are able to observe the ammonia. So in this way, we can always understand different kinds of processes using the ab initio molecular dynamics, which will be complementing, and in sometimes they are superior even to the electronic structure methods like DFT that we are generally using. So here is another example where we have used the water gas shift reaction, but I'm skipping this part. So moving on to the other electronic structure method applications, we have seen in this particular example, we tried to understand the reaction mechanism of a supramolecular assembly that was synthesized by our experimental collaborators. So this supramolecular assembly resembles or mimics the carbonic anhydrase activity, where carbonic anhydrase is a enzyme that is present in various organisms, including humans, and its main purpose is to convert that CO2 which is there in our blood, and it will convert it into the bicarbonate as well as the protons in the presence of water. So it actually regulates the pH levels in our body, as well as it will help us to just exhale the CO2, and so that it can pump the CO2 from the blood into the lungs. So here,
across 20 minutes.
Okay, thank you. So this is one of the examples where we have used the electronic structure methods in order to understand the exact reaction mechanism of this assembly in order to exactly reproduce this carbonic anhydrase reaction mechanism, ester hydrolysis mechanism. So I'm skipping 2-3 slides because these are other examples of where we have seen how to unzip the carbon nanotubes and how to understand the layer dependent band structure and various other graphene and similar kind of materials and their optical and electronic properties. So moving on to the ongoing research at the IITM. So here I have majorly concentrated after coming here 2 particular projects. The first one is on the understanding the solid-electrolyte interface that is formed on the calcium surface, and another one is to understand the dissociation of the perfluoroalkyl substances. So in this particular project, what we understood from the very recent experiments that were performed in April or so is, like, whenever the salts containing boron atoms are there, so then this calcium can be reversibly deposited on a calcium anode. This is what we have learned from the experiments. However, simultaneously, the experiments have also shown that if there is a salt like TFSI2 or something, they cannot reversibly deposit. So only boron containing salts can reversibly deposit. Moreover, if we add boron additives, then these salts which can on their own cannot deposit can also be deposited now. So the addition of boron is doing something to this interfaces is what we learned. So in order to understand that, we started simulating with both CaBF, so various kinds of, so CaBF4 twice salt as well as the CaTFSI2 salt. These 2 salts we have considered, and we started understanding the solid electrolyte interface that is formed here. What we understood was, like, the CaTFSI2 salt is automatically dissociating due to the high reducing power of the calcium, whereas CaBF4 is not. In order to further understand this, we tried to fix the CaTFSI2 salt first. So since the experiments have already observed that after a few cycles, if you add the boron additives, CaTFSI2 can be useful. So we fixed the salt and we studied it further. And here also we understood that once you fix the salt first and then release it, then already the Ca layer that can reduce is reducing the solvent and it is leaving the salt as it is. So this is one work which we are continuing in order to further understand the calcium migration. The other one is to find the suitable metals in order to decompose this perfluoroalkyl substances which are harmful pollutants. So we did find that based on our experience with the calcium ion batteries, when we use the calcium metal, it can be easily degrade. We can easily degrade this PFAS material. So this is also an ongoing work. And with that, I'm going to the possible areas of collaboration. So we definitely need help from the experimentalists in order to study the degradation of perfluoroalkyl substances. These will be very important things very soon. And the other place where we are interested in collaboration is with the programmers who can port our MEIMD codes onto a GPU or FPGA architectures. Of course, we are happy to collaborate on other areas such as battery technologies, catalysis, etc. I just want to thank all my group members. The calcium ion batteries work is being done by Subdeep Banerjee. He's one student, one of the PhD students. And with that, I would like to thank you all for your attention.
Fabulous. I mean, Chaitanya, you exposed the right amount of science with the right opening for collaborations, expanding into energy, water, environment, materials, a number of areas. Now, let me ask one or two questions and then keep this open. We have about 7 minutes left for questions. So glad. You talked about electron transfer dynamics, especially when it comes to transfer dynamics with a given molecular orbital, molecular specificity in this. Now, how do I experimentally probe that to a specific molecule? Of course, you could probably think in terms of energy tuning, etc. But you are looking at the overall relaxation dynamics. Experiments see that overall relaxation dynamics. So, what's your thought on that?
So what we are here doing is actually an approximation, because the real system will not be staying in any of these molecular orbitals. Probably, as you pointed out, this will be somewhere like S0, S1, these kind of states. So here what we are seeing is like we are trying to approximate that S1 state as the LUMO of one of these molecules, and then we are trying to see the dynamics. And also we are in a single particle picture, that is like only one electron we are simulating here. So in reality, we need to also include things like electron-hole interaction, and we need to consider all the other electrons as well. But that is a little bit more difficult thing to theoretically capture at this moment. So the
second thing was in the context of the slide number 18 or so, you were talking about changes in the system, in the whatever is the interaction that is happening with collisions or with encounters between two molecular systems. You are probing that non-adiabatically, very, very good. But the system is undergoing changes, such as, for example, a metal involving something. There can be unteller distortions. As these things happen, as these interactions happen, there are changes. Along with those electron dynamics events. Can I see that structurally? Can I correlate these structural changes as well? How do I do that with your codes?
With my code at this moment, we cannot, because I mean, we can at least for as long as on the single potential energy surface we can, but once we are going on beyond one potential energy, that is this non-adiabatic level, we cannot, because I did not include the electronical non-adiabatic influence onto the nucleus. So that part we cannot capture. But as such, with single potential energy, we can definitely understand how these nuclei are moving, or how, for example, as you mentioned, the Untitled distortion or something, that we can definitely correlate.
All right, let me move on to others in case there are questions.
Yeah, this is Kannan here. Can everyone hear me?
Yeah. Yes, Professor.
Yeah.
Please go ahead.
Right. Yeah, very nice talk, and definitely it would fit into some of the areas which I'm working on currently. It will nicely complement my ideas. So what I would see is one possible application of your DFT simulations would be photocatalysis, where I think by shining the UV light on the titania catalyst, you can achieve higher degradation of the different dye molecules. So I'm working on wastewater treatment involving textile dyes. So what catalyst to use, and what dopants we can further add, what should be the composition of titania, all these things I think I can experiment, but by trial and error. But in order to do it in an informed way, given the thousands of combinations of possible atoms and different transition metals and so on. So I was wondering whether the DFT and the modified versions of DFT will be able to help me make an informed decision, so that I can narrow down the number of options to a few, maybe 5 or 6, which I can try and then optimize.
So yeah, definitely. So as long as like we are dealing with the DFT level, then that is possible. At least if you are considering one particular material, for example, TiO2 you mentioned. So with that, if you have several configurations in your mind, so then we can scan them and we can at least do the band alignment, and we can see which ones would correspond to the right material for your specific application, which is
but Chaitanya, quite a bit of such work has already happened in terms of what is optimizing, etc. But overall, developing a kind of a combinatorial program as to what is rightful experimental synthesis. This has happened in superconductivity. This has happened in several other areas as well. You are aware of this, and so yeah. But then there is a lot of possibility. Let me take 2 other questions, Kannan. Let me move on because there are other questions as well. Soumya, you have a question, and followed by Sanjeev.
Yeah, thank you. So Chaitanya, it's a very nice talk, and especially I'm quite interested in this organic photovoltaics, which you do on a regular basis. And probably Venkat also will be interested, because we are doing in collaboration this work. So I have one small question. Maybe we can discuss further in offline. Very interesting thing. So slide number 16. We're showing some initial condition of that I as 0 equal to LUMO. So why this donor of the LUMO is important? Because it's when it's donating, I suppose it is from the HOMO, right?
Yeah. So, but what we are trying to simulate is that after the excitation has happened. So now your electron after excitation is in general should go to the LUMO of the donor molecule, and we are just simulating with the single electron. So now once this electron goes to the LUMO, from there we are trying to see how it is moving down. So this is what we have seen. So here this LUMO plus 3 corresponds to the LUMO of the donor, which is the H2PC in this case. And how that is finally coming to the LUMO is what LUMO here corresponds to fullerene LUMO. How it is transferring is what we are seeing. So we are just considering
it is going through the excitonic states, right? So how you are
we are already
confused here.
So we are assuming that the electron is already excited. So from that,
no, I'm not talking about the excited. I'm talking about exciton.
Yeah. So we are only considering the electron as I was answering to Pradeep. We are only considering electron, but the next level is to also include the electron-hole interaction. So those interactions are absent here at this moment.
Okay. I see.
Thank you. Sanjeev, you have a question.
Thank you.
Look on.
Yeah. Hi, Chaitanya, very nice talk. So my question is, I think one of the enzyme we had talked about the carbonic anhydrase, if I'm not wrong.
Yeah.
So for enzymatic reactions such as this, so at what level do I describe my protein?
At what level? Sorry, I could not hear you.
I can describe my protein. It's you must be describing in an implicit way, right?
So I'm actually simulating this ZnPA2 assembly. It's not the anhydride. I'm not simulating the enzyme here. I'm just simulating the supramolecular assembly that they have synthesized, which is mimicking the carbonic anhydrase here. So I'm just simulating this part, which contains a zinc atom and the other.
So in any way, do you have a background effect what enzyme might impart on this whole reaction?
As I said, this is, no, I don't have, but as I trying to mention, this is not an enzyme simulation. This is supramolecular assembly that is mimicking the enzyme. Probably I was not
like we do in QMMM, that we basically take the presence of protein in an indirect way. That is not there at the moment in your system, that we can get the implicit presence of the enzyme. Not yet, right?
Not yet, no.
Thanks.
Pradeep,
Yeah, we should move on.